yeah, so we'll talk about confinement and supersymmetric Young's theory in the lattice.
Thank you. Thanks to the organizers for this nice workshop. Actually, Andreas has invited me here to present some summary of the lattice results of supersymmetric Yang-Mills theory and also theories with adjoint fermions on the lattice, which is a rather broad topic. So what I decided is to make rather an overview and review some of the results that we obtained here. And we can then later on, if you want to know some more of the details of the results, ask some further questions. So actually the talk will be 3 parts. The first part, I will just talk a little bit about continuum, supersymmetric Yang-Mills theory, and also the relations to other theories with adjoint fermions. And then I will talk about or review and summarize the lattice results of supersymmetric Yang-Mills theory. And in the end, I will talk a little bit about an ongoing project of investigating the semi-classical confinement of supersymmetric Yang-Mills theory or Yang-Mills theory in general. But let me first start with introducing theory. So the supersymmetric Yang-Mills theory has mainly been considered as part of beyond standard model supersymmetric theories. But later on, it was also a toy model for understanding better the confinement mechanisms. There are analytic calculations of condensates and beta functions, etc. And then there's also this orientifold planar equivalence, which relates this to QCD. So there has been a lot of development in the theoretical understanding of this. And then later on, there was also by Mithat Ünsal and other people in more deeper investigations also of the semi-classical calculations of the compactified supersymmetric Yang-Mills theory, and also in general in these considerations also the semi-classical analysis of the theory plays a major role. The Lagrangian looks similar to QCD. The main difference is that we have now just one flavor of Majorana fermions in the adjoint representation, which makes it in some respects similar to pure Yang-Mills, but in others more similar to QCD.
Motion on Majorana, for example, it's not simply continuous to integer. So if you are going on the ingredient later, then they would say that it will be a problem. Right?
Yes, there's a principal problem about this, but there are first of all theoretical arguments how to deal with that. And I can talk about this later because this is goes in some of the details of the whole derivation. Basically, you can try to the fermions are usually integrated out, and then you can somehow just look at, for example, the spectrum of the theory, and then you can take what, for example, half of the eigenvalues, and this corresponds then to something that you can connect to Majorana nature. But this is already something putting the theory on the lattice, some complication. The important properties of low energy or low temperature supersymmetric Yang-Mills theory is that it is expected to have a QCD-like running of the gauge coupling from to be a confining theory, and then also you expect that you have gluino condensation and chirosymmetry breaking. Since supersymmetries should be preserved even at low energies, there should not be any kind of spontaneous or anomalous supersymmetry breaking. Therefore, there must be some multiplets of bound states that describe the low energy effective theory. And the simplest possible way to arrange these kind of bound states is a chiral multiplet. So this means we need a scalar, a pseudoscalar, and a fermionic particle that all have the same mass to describe the lowest bound states of the theory. In the literature, there exist basically two suggestions for these kind of states, which are either gluino balls, which means meson-like states, and then you have also the possibility that these are just glue ball states. And then you have a combination of the fermion and the gluonic particle, which is possible in the adjoint representation, which makes up the fermionic content. So this should be the low energy effective degrees of freedom. So yeah. We don't. So actually I've written it here already, there is an expected mixture between these two. And there's even the difficulty that on the lattice, this mixture can be different from what you expect in the continuum. So it's really difficult to tell one of these from the other apart. But in the literature, there are some discussions whether the lowest multiplet is rather of one or the other type. So but I don't know. Yeah. So you have only quantum numbers to tell states apart. So therefore, it's difficult to you cannot really distinguish them in a gauge invariant way. So one remark I want you to add is that if you increase the numbers of flavors in and going away from supersymmetric Yang-Mills theory, you have to be careful because as everyone knows, is that for a large number of flavor, you lose in a general QCD like theory, you use asymptotic freedom. And then there's even a lower range, which is called the conformal window, where you expect that the running of the gauge coupling changes and it develops a conformal fixed point in the infrared where the running stops. And the important point here is that for the adjoint fermions, this number is much lower than for the fundamental representation. So if you compare supersymmetric Yang-Mills theory results, then for example, with lattice results in which have a larger fermion content, it can be that you are in a completely different regime. If you just look at perturbative estimates, I think the asymptotic freedom is at around 11/4 is the estimate where it is lost. And for the lower end of the conformal window, of course, you don't have any perturbative perturbation theory is not reliable, but the estimates are that this is either just above 1 or just above 2, depending on what kind of methods you are using. What lattice results indicate is that actually the theory with 2 Dirac fermions is already in the conformal window. And the reason why this theory has been so heavily investigated, so I listed here only a subset of all the lattice results that are available for this theory, is that because it has been suggested as a minimal walking technicolor extension of the standard model, and therefore it has been heavily investigated. What we also did, so Andreas Biaggiolini and others, is to investigate the theory with one adjoint Dirac flavor. And this turns out to be very difficult, and it's still not clarified whether this is whether this still shows a conformal behavior. You have to remember that on the lattice, if you are studying this kind of slowly running, you are limited by the scales. So you have only a window between the scale given by the lattice spacing and the lattice volume. So it's rather limited that what you can do, but we are still studying this, and there will be shortly also an update on the results concerning this one flavor theory. What I can say is that actually a large number of lattice results for all these kind of related theories exist. So we have lattice results for, I called it here half a Dirac flavor. So this is supersymmetric in this theory. Then for the one flavor, as I mentioned, then also for 3 halves, which are 3 Majorana flavors, and a large number of results for 2 flavor. But even for theories with a mixture of adjoint and fundamental flavors, there are already some. Yeah, I mean, this is the ultimate goal. So to extend the results for the beta function on the lattice so much that you can match to the perturbative results in the UV.
Right. Then you know what you get the number of flavors on that side.
Yes, but this is only valid if you go at the upper end of the conformal window, where you lose asymptotic freedom. The lower one is so the lower one is controversial because this is really in the non-perturbative regime. Yeah. Yes, but for so all kind of approximations indicate that for the adjoint representation, there's only a very small NC dependence. For the fundamental, it's of course different.
I wouldn't expect to get a dramatic, but not to me as a temporary object.
Yeah.
What number of flavors is divided? But there's no control. Now, that's a bit drastic. Take the largest value, which is not a degree. I think that I think 5 out of.
Yeah.
So depends on how reliably. It's not. Well, it's not parametric.
Yeah. I mean.
I think it's okay. I believe that that is full.
Yeah, no, I mean it's a very difficult calculation, and also various other methods besides lattice simulations have been tried. For example, Schwinger-Dyson or FRG studies to fix this, and therefore you have also different estimates. But yeah, I mean, no one knows how reliable they are.
No. Unimaginable.
Yeah.
For such small flavors. So that's 4 now.
Yeah, it's 4 Majoranas. So you so.
I think yeah, again, doesn't sound like that.
So yeah, it's actually, if you increase here the number of flavors, it's only very tiny. So I mean, between if you just take the perturbative estimates, it's something just above 2, and then the upper limit is 11/4. So yeah. So it's a very tiny range of flavors. So the other thing I also want to mention is what happens to the confinement-deconfinement transition in supersymmetric Amuse theory. And of course, like in in Young-List theory, you expect a certain deconfinement transition. And the good thing is that if you add the adjoint flavors, they don't break center symmetry. So you have a deconfinement transition that is valid for any kind of fermion masses that you can determine reliably. The additional thing is if you go to the massless limit, then as like in massless QCD, you also have spontaneous chiral symmetry breaking. So you have in principle two different transitions, which is a chiral transition and a deconfinement transition. And there have been estimates by, so there are calculations and considerations of 't Hooft anomaly matchings, and these give a bound for these kind of transitions, namely that the chiral transition should be above the deconfinement transition. Usually in some papers for supersymmetric Young-List theory, it is considered to be the same, but there is no necessary proof of this. Now, if you consider fermions with antiperiodic boundary conditions, so the normal thermal partition sum. But if you now switch to periodic fermion boundary conditions, then you are investigating a twisted partition function, which is in fact nothing but the famous Witten index for supersymmetric theories, or more generally, you can call it a twisted partition function. And what it counts, because of this additional -1 times this fermion number operator, is the difference between bosonic and fermionic energy levels. And since all states except the ground state in this supersymmetric theories cancel between bosonic and fermionic states, it just counts the difference between bosonic and fermionic ground states. And since for supersymmetric Young-List theory, this is a fixed number, just a number of colors, that correspond. This twisted partition function is independent of the radius r here. Now you 1 over temperature has to be replaced here by this kind of radius, because it's rather a compactified theory than a finite temperature theory. And therefore, in this compactified theory, no phase transition is expected as long as you have this periodic fermion boundary conditions. This has been studied in quite some detail. So even for larger number of adjoint fermions, and you can show that in all cases, if you just look at the perturbative effective potential for the Polyakov line, phases, then you find that the perturbative contributions from the gluonic fields are counteracted by the adjoint fermions. And therefore, if you consider a larger number of flavors than in supersymmetric Young-List theory, you immediately will see that you end up in a confined phase if you consider periodic fermion boundary conditions. More precisely, one has to be careful how this confinement really appears here. Usually at strong coupling, the confinement is that the Polyakov loop averages to 0 appears because of large fluctuations of this Polyakov loop, which are, so to say, just given by the Haar measure of the theory. Whereas in the perturbative regime with a larger number of fermions, you get fluctuations around the configuration of the Polyakov loop eigenvalues, which just puts you to a 0 Polyakov loop. And therefore, usually these kind of two different reasons for this confined regime are called non-abelian and abelian confinement in some works. What is important is that the specific case of supersymmetric Young-List theory is quite distinct from the ones with a larger number of fermions, because there you have an exact cancellation between the perturbative contributions of the fermions, of the adjoint fermions and the gluons. So basically this means that from this perturbative perspective, the theory remains closer to a strongly coupled regime. Yeah, even at this small compactification radius. This has also been a motivation to study these theories in a semi-classical regime, because you can apply this semi-classical method at a small compactification radius. And it was conjectured that molecules of fractional topological charged object should be responsible for a confinement in this kind of regime. So these were just results from the continuum investigations of supersymmetric Young-List theory. Now we want to study this on the lattice to get some further insights. And we also want to see whether we can match these theoretical predictions and first of all confirm in that way that we can reliably simulate the theory, and then also look at, for example, how reliable this semi-classical description of the confinement is, and whether one can extend these kind of conjectures about the confinement in supersymmetric Young-List theory. The problem here is that if you formulate the theory on the lattice, any kind of local lattice formulation breaks supersymmetry. This is unavoidable for any kind of theory that you break supersymmetry on the lattice. So it can only be recovered in the continuum. And in addition, there are some additional practical and technical challenges. We had we already mentioned here the Pfaffian and the Majorana nature of the fields, but I won't go into details here concerning these kind of more technical problems. Yes, but then, yeah. This works only for maximally supersymmetric theories. So for n equals 4, you can go to this twisted formulation, and then you can preserve, because you need to have some kind of scalar fermion. I'm not aware of this. I only know the construction for n equals 4. So for 2 dimension it works, but yeah, of course. But for 4 dimensions there is. Yeah, maybe we can discuss it afterward. The thing I just want to mention here is that if you formulate the theory on the lattice, you have to be careful with 2 different kind of symmetries. First of all, supersymmetry. I already introduced a gluino mass term, which leads to a soft supersymmetry breaking. And then you have also a chiral symmetry, which is in case of supersymmetric Young-List theory, first of all, broken by the anomaly, but in contrast to bond-flavored QCD, you have a discrete subset of the symmetry which survives this anomalous breaking, and then you have spontaneous breaking due to the presence of this gluino condensate, which makes basically the chiral symmetry breaking in supersymmetric Young-List theory. Now you formulate the theory on the lattice, and this does spoil all of these 2 symmetries. So you break chiral symmetry and you break supersymmetry if you use the most efficient formulation, which are just Wilson fermions in this case. So you have to recover supersymmetry in the continuum limit, and in this quantum field theory, you have, of course, to do some fine tuning. So you have to add counterterms to the action, and then tune the signals, tune the coefficients according to signals for the restored symmetry. in supersymmetric Young, in n equals 1 supersymmetric Young's-Mills theory, this fortunately turns out to be very easy. So first of all, chiral symmetry is actually similar to also what you would do for simulations with Wilson fermions and QCD. So you would have to tune the mass towards some critical value where you recover the symmetry. The good thing is that you can analyze now the supersymmetric Ward identities and all kind of operator mixings, and you will find that in that case, the same tuning of the same parameter is also enough to recover supersymmetry in the continuum limit. So you end up with basically doing the same thing that you would also have to do for QCD. With one additional difficulty, which is to define a chirosymmetric point, because we don't have the same chirosymmetry as in QCD. But what we have seen is that you can use a kind of signal which corresponds to an adjoint pion mass. It's a counterpart to what would be the pion in QCD, and tune the signal according to this. But we later checked also that this is consistent with supersymmetric Ward identities. Actually, the fact that chirosymmetry is enough to recover supersymmetry in this series also means that if you have some formulation with chirosymmetry on the lattice, like what's called Ginzburg-Wilson fermions, then you don't need any kind of fine tuning. But these kind of fermions turn out to be very expensive to simulate. Therefore, they are usually not enough to extract some information, especially for the bound state spectrum of the theory. So the first results I want to present here are the bound states of supersymmetric Young-Mills theory. And what you can see here is basically a scalar particle, then a pseudoscalar particle and this fermionic particle. And as I told in the beginning, we expect that they should all have the same mass. And here you see two different kind of extrapolations to the continuum limit, just assuming a kind of dependence on lattice artifacts because we use a certain improved action. And you can see that in both cases within arrows, you get a coincidence of these constituents of this chiral multiplet. So this means yeah. Yeah. So basically here you see that this is in some units the lattice spacing, and you see as you approach the continuum limit, then you recover this multiplet structure.
Yeah, but so there is no way to the procedure which would be consistent with symmetry of each state.
No, I mean this is unavoidable. So unless you have this kind of twisted formulations, you either end up with a non-local lattice formulation or you have to break supersymmetry. Yeah. No, both are SU3 because this is order A lattice artifacts assumed, and this is order A squared lattice artifacts. We have added some improvements which reduce this order A lattice artifacts, but we are not completely sure whether we have removed all of them. Yeah.
Are there any sign problems?
Yes. So in principle, there is a mild sign problem here, which is also due to the fact that there are Wilson fermions used. So we can measure the sign of the Pfaffian, and we can just use a reweighting procedure. And in fact, for all of these results that are shown here, because we use improved lattice formulations, it turns out that this is a negligible factor, because it's it's so to say in a regime which is very close to the continuum. Okay, we have done further extensive studies of these theories. So we have determined the static potential as shown here, for example, for different, so this kappa means is just some inverse mass parameter. And so for different kind of masses, you can also measure the string tension of the theory and then extrapolate this to the supersymmetric limit. We have also done investigations of the running gauge coupling, which one example is shown here, where you can see that it indeed shows some QCD-like running. We have also confirmed this restoration of supersymmetry using supersymmetric ward identities, which is important because we use this chiral symmetry approach, and one has to really confirm that everything works consistently here. And we have also, there are also several determinations of the gluino condensate in supersymmetric Yang-Mills theory, which provide quite consistent results. There you have to be careful that some additional methods are needed, because with Wilson fermions you get some not only multiplicative but also additive randomization. So you have to use some methods to determine this, or you have to use domain wall or overlap fermions. But this has also been determined and measured. And we have studied the finite temperature transition of supersymmetric Yang-Mills theory. Well, this is a kind of energy scale, and this is the effective coupling. This is, yeah, I can tell you more details about the scheme, but yeah, so this is related to some gauge fixed vertices that are calculated, and then the momentum dependence is extracted. But we have also used other methods. Okay. Yeah, for any of these things, we can discuss also details if you want to.
What is confinement scale? Is X in what would you say confinement scale is? Muscle.
We have determined also some lambda parameter that you can also define in the scheme. I can show you the details, but it's yeah. I just wanted to here summarize some of the results. I can later on show you the references and explain a little bit more about it. Okay. And the last thing I wanted to talk about, okay, is investigations of this compactified regime of supersymmetric Yang-Mills theory. So what you can see here is the expected phase diagram. As I said, the Witten index basically fixes to no phase transition here in the down to the semi-classical regime if you compactify the theory. And if you increase the mass, then at a certain point, there is some even calculable phase transition expected. And then this should connect to the Yang-Mills theory transition, of course, for infinite mass. This can be investigated on the lattice. And what we find is actually quite interesting, that in contrast to the thermal case, where you always have this deconfinement transition, the Polyakov loop rises at a certain point, that with periodic boundary conditions, if you lower the mass at a certain point, you see this kind of continuity. What is different from the expectation is that you get actually 3 different phases. So you get a confined, a deconfined, and a reconfined phase if you go to larger masses. So this means that on the lattice, we obtain basically such a phase diagram at very low masses or high kappa, which then you end up with something where you don't see any phase transition, but at larger masses, you basically see some kind of intermediate phase here, which corresponds to an intermediate deconfined phase. So this is different from what is expected for the phase diagram, somewhat different. One can do further investigations, and one sees that basically in this regime where you go along this line here, then the theory stays basically in something that looks like a strong coupling phase. So the phase of the Polyakov line, of this Polyakov line eigenvalues basically fluctuates only given like from the Haar measure. But then at even smaller radius, then you see something that looks, that is a continuous transition to something which looks like abelian confinement, so something that fixes the Polyakov loop to something that that stays in the, that fluctuates around some configuration that is confined. We have found the reason for the difference between the this continuum expectation and the and this lattice results in the lattice artifacts which are introduced by Wilson fermions. Basically, if you go along this line here, you reach at a certain point a scale where the radius, where the lattice spacing becomes not negligible compared to the radius, and therefore it sees what is called the doubling modes in this Wilson fermion formulation. So if you effectively see a larger number of fermions than you have, and therefore you can even use lattice perturbation theory to calculate then here this transition line in this regime here. So basically what you have to do is you have to go up to a certain scale here, and then you have to decrease the lattice spacing if you want to have a reliable regime if you go to smaller rate. But otherwise, basically this semi-classical regime can be reproduced quite nicely in the lattice. Yes, yes. So basically what I would expect here is that this transition goes lower and that this line here continues and then becomes what is expected from. Yes, so basically, yeah, there's some kind of trivial scaling here. But I mean, you will never completely have something that, at a certain point, you will always reach the scale here. Yes, yes, but actually this phase there is not so different from, it's still a confined phase, it's just a larger number of fermions that I think. So the latest thing that we have tried to study or started to study in collaboration also with Antonio Gonzalez Arroyo is to find some methods to get more insights in the semi-classical regime and maybe identify certain topological structures. And therefore, you have always the problem, of course, how to define topology on the lattice. And one usual method is that you use some cooling or gradient flow to smoothen the configuration. One additional method, which I found quite interesting, is that you also can use an adjoint zero mode of the adjoint Dirac operator, which gives you, if you have a background field that gauge field that is a solution of the equation of motion, gives you something that you can relate then to the topological density. So you can extract basically the information about FF dual just from this zero mode. There are some difficulties to formulate this on the lattice, but these techniques have been developed also already in previous situations there. And here's shown one example where you basically start with such a configuration and then you can reliably extract these topological. This is basically the same configuration, but yeah, this is the topological charge distribution. Sorry? This is a snapshot. So you project the lattice, you take to one slice to a two-dimensional plot, and then you plot this topological charge density. And then the information that is hidden behind this noise is basically shown here. So basically, yeah, I mean, this in both cases is of course 0, but these are artificially, this is an artificial construction still. It's not a simulation so far. So this, you put these instantons in, then you add some noise, and you see whether you can re-extract it. Yeah. Yeah. So yeah, I skip this further things here. And yeah, I just, yeah, the summary is that basically we have a large number of results already, and an open problem is still this, the lower end of the conformal window, which is also important for other theories here. And we are also have added scalar fields to the theories, but the problem there is to find some tuning which gives you, which can give you supersymmetric QCD or n equals 2 supersymmetric anomalous theory. Yeah, thank you.
Hi, but maybe we take a couple of questions, maybe we just have like a 20 minutes. So, yeah. Were they started from what? The confinement is the EPS here, is the European amount?
No, not so far, but yeah.
Yeah, we'll be discussing.
We are already discussing. Okay, but this is for the compactified theory, or is it also true for the?
There's no central charge that we make.
Okay.
Yeah, just wanted to a couple of comments for, I think for one, grand bill, there is, I think, qualitative gravity rule or gravity rule.
Yeah, but yeah, but it's not that well established as for any 4 as I. But if you have some.
There is there are findings that ground that qualitative.
Okay. Hey, we can discuss that.
Also, I think one tries to say two-dimensional and no physics with one.
Yes. Well, there are some results for two-dimensional Young-Mills with adjoint fermions, but yeah. So there's only, I think there's only one lattice proceedings, and there are some results of n equals 1 supersymmetric Young-Mills theory reduced to 2 dimensions. Not that one.
Not that. SU and Young-Mills. Yeah, ideally one.
Yeah, I mean, yeah.
I tried looking at it. That's what I'm.
Yeah, I mean, we have started to look at this as well, yeah, and the only reference that we found was some lattice proceedings, but not a complete analysis. Okay.
there any understanding when the component of the kernel can do operation from the variable side?
So there are arguments by Witten, I think, which are string theory motivated, have been made that this should be the same. And then there are also some kind of effective theories developed by Uwe Jens-Wiese and others, which describe this transition. Yeah, so you have before the different vacua of the condensate, and afterwards the different vacua of the Polyakov loop, and then the domain walls. From the domain walls you get the domains, these new phases. So there is some kind of effective theory argument. I can show you these references.
No, but I haven't got is there any difference between SQL and the
Well, for supersymmetric Yamous theory, we investigated both, and at least the particle spectrum, and it in some units of the string tension, actually the low state looks similar, but so for the conformal window, I think there are not really studies of larger NC. It's focused on SU2.
You said that state of NF equals 1 is still unfolded. And the other